My name is Alex Bretman. I'm one of the co-conveners here with Eileen and UGeN and Christian. I'm currently doing my master's in geology at the University of Utah. And so I get to introduce Grant and Ian today. Grant's in my cohort, finishing up his master's as well this spring. And then I've connected with Ian just by being in the proximity of doing geothermal geology in the Great Basin. So yeah, Grant is currently a master's in geophysics at the University of Utah. He's working with Dr. Chris Pankow on the behaviors of induced seismicity down at Forge. He has a bachelor's from the College of Charleston, South Carolina, and he will be defending here in about 6 weeks, wrapping it up.
Yeah.
So, cool. Grant, thanks for giving a talk today. Yeah. I think you should be good to go. On screen.
Yeah, very good, Grant. If you don't mind using the pointer, like for people online to see where your pointer is.
Welcome to awesome. Yeah. But yes, yeah, thank you guys for having me here today. Yeah, I'm Grant Spraker, University of Utah. And so, yeah, I'll be presenting a talk on migration patterns at the University or at the Utah Forge project involving evolving triggering mechanisms after the injection shut-in. Yeah, I pulled a fast one on you, Alex, changing up how to talk, but just means you guys get some new stuff today. So, brief introduction, if I'm sure most of you guys are familiar, but Utah Forge Project is a field-scale laboratory down in Milford, Utah, that tests and develops technologies for enhanced thermal systems. They, in the past, have had multiple successful simulations and circulation experiments. Some of the most relevant tests include the 2024 stimulation, in which 2 fracture zones were discovered from the microseismic activity, and the 2024 circulation activity, which will be the focus of this study. It included a month-long circulation test to test the heat extraction and fluid recovery of the system, and we monitored the seismicity with a network of 6 near-surface seismometer stations. So, goals of this study was to cluster and relatively relocate the 2024 microseismicity to sort of map the continued fracture growth of the system, kind of like branched off of those 2 previously identified fracture zones, and then to assess the potential microseismic hazard associated with these new fracture planes. We then look into the behavior and mechanisms of the microseismic migration that occurs both during circulation and following the injection shut-in. So the algorithms that we use include both clustering and growth. So what we do is look at the network similarity of the microseismic events. So those events with similar waveforms are clustered together, relatively relocated into tighter planes, in order to sort of like highlight those geological structures that are like located in the reservoir. We then, we relocate the catalog of both the 2024 and simulation and circulation catalog together. This just like helps get a better constraints on those locations, improving the absolute locations to really ensure that the pre-existing geological structures are mapped out properly. We then go through a principal component analysis to reduce the dimensionality of the microseismic cloud. This just like helps pick out those fracture plane bits easier. And so our first sort of like key finding is a 2.5 kilometer fracture growth off of fracture zone 2 that is a reactivation of a pre-existing fault. So this is the 2024 stimulation microseismicity. This was mapped out by Peter Nemes during one of his during that previous stimulation. And these green events are the microseismic events located during the 2024 circulation. And so you can see in that map view, we have a almost like direct continuation off of fracture zone 2 going down to the south, and it is a slight continuation going off of fracture zone 1 towards the north. Bit of a zoomed out view. This is again the 2024 simulation microseismicity. We have like a maximum lateral extent of about 1.5 kilometers around the injection wells. And then the 2024 extended circulation seismicity is a significant increase to what we saw. We see about 4 kilometers of lateral extent extending mostly to the south off of that fracture zone 2. We also pick out two subfracture zones, 2A and 2B, that are kind of like highlighted here, which we identify as the pre-existing fault that was there. That fault acts as like a conduit for fluid flow, making it easier for the electroseismicity to progress along that existing zone. And during the circulation, we had about close to like 900 microseismic events that were eventually relocated, all between magnitude -1 with a maximum magnitude of about 1.19. So nothing too crazy that has come up there just yet. And all the events are colored by time. As you can see, we have like an injection that shut in about like halfway through this sort of like map seismicity, kind of like stopping around this main southern branch going down to the south. And this figure here just kind of like highlights and emphasizes more of the seismicity that occurs after the shut-in. So all these red events occurred after we had stopped circulating fluids. And it's primarily concentrated in that fracture zone 2, suggesting a sort of like a change in like triggering mechanisms that happens after we stop pumping fluids. Again, some further evidence just showing some more reactivation of fracture zones. We go through a different clustering, putting together events of like highly similar waveforms of that combined stimulation and circulation catalog. So we have like two main clusters, clusters 0 and 1 here, that exist both in the fracture zone 1 and fracture zone 2 that I just showed. So this just emphasizes the point that we are, reactivating those same similar reservoir volumes in both the 24/4 stimulation and the circulation. And so moving on to our next key finding, the subfracture zones 2A and 2B are highly planar. We go on to estimate potential maximum magnitudes that could be produced by those fracture planes. So the principal component analysis, each of those fracture zones are, represented by 3 characteristic eigenvalues, and those 2 largest ones are used to represent the fracture plane that just sort of encompasses those different sections of the microseismic cloud. We test the planarity of those, just following the ratios of those those characteristic eigenvalues. And while each are planar, fracture zones 2A and 2B are especially planar. And being so, increases the likelihood that each one could act as a single fault plane in the case of a full fault rupture, as circulation fluids reduce the normal stress on those planes. So this leads us to calculating those potential maximum magnitudes that could be produced by each fracture plane in the case of a full fault rupture. And what we find is that fracture zone 2A, being the largest, could produce a moment magnitude of 3.2. Fracture zone 2B is 2.7. Fracture zone 1 is 2.9. However, we aren't too worried about fracture zone 1 because in another study by Ryan Schultz, he shows that fracture zone 1 exists in like a exhibits behaviors of a bound system, meaning it does sort of have a maximum magnitude upper limit to it. However, fracture zones 2A and 2B, because they exist on some sort of like pre-existing fracture faults, the potential seismic risk and hazard associated with them is a bit larger, and caution needs to be taken into account in the future. However, our final key finding is the evolving migration patterns and triggering mechanisms before and after injection shut-in. So we look at the wellhead pressure data, as well as the cumulative injected volumes and the seismic rates. So the 2 most important curves here are the cumulative remaining fluids in the reservoir that increases throughout the circulation, and then also the cumulative number of seismic events that occurs throughout the circulation and thereafter. What we see is that as the fluids are circulated throughout the system, some become trapped due to the pre-existing faults, and that in turn increases the amount of seismic events that we see throughout the whole injection sequence. And we attribute that to activation and reactivation of the pre-existing fault. However, you can notice that there is a slight delay in the timing of the injection and then the timing of the increased seismic events. We assume that delay in increased seismic activity is due to the aseismic reinflation of those pre-stimulated reservoir volumes. So because we've already kind of like, fractured the area around the wells, it takes some time for the fluid to sort of like encompass and refill that volume before we start to see more microseismic activity in the outer regions. And then during the whole circulation, we increase seismic events at a relatively steady rate. And then following the shut-in, that seismic rate still remains constant for about 5 days following the shut-in. And we assume that, or we attribute this to the fact that those highly pressured fluids are still trapped within the reservoir. It takes some time for those fluids to be accommodated by the increasing area of like the fault zone. However, when that does happen, we start to see pressure decrease, which, as you can see in those blue and red curves, it goes down gradually. So pressure decreases, there's relaxation along the fault, and then we attribute this to a changing triggering mechanism. The pressure relaxation is like causing the majority of the seismicity after this point. And then later on, very much later in the seismic recorded events, we start to see that sort of like upward migration due to that fracture zone 2B that I showed later. And we assume that this is some sort of other sort of like a buoyancy forces acting on those trapped fluids, kind of like forcing those fluids and then later the seismicity up into that fracture zone 2B zone. So there are most likely a couple of different triggering mechanisms like going on all throughout the circulation and injection shut-in afterwards. And we can also kind of see this in the migration patterns. So here we have the purple events are fracture 1, orange are 2A, and red are 2B. And so what's important here is during the circulation, we see clear continuous, microseismic migration away from the injection well over time. And that sort of like upper limit is defined as the trigger front of the seismicity. And this follows a diffusion pattern with a diffusivity of about 0.25 meters squared per second. And it continues to do so for about until that timing of like 5 days after the injection shut in, where you can see these darker lines begin to end. And this lower bound is the back front, and we see it began after the injection shut in. And it follows the same sort of diffusivity pattern, that same rate. And what's interesting, we do see diffusion patterns pretty commonly in injection studies and injection swarms. However, in most cases, the back front has been noted to like develop during the circulation or injection of fluids into the system. So it's interesting to note that ours clearly develops after the shut-in. In 2 other cases, one in Basel 2006 and in Vancouver Basin 2012, they also see a post-injection back front. And what's interesting to note about that is they also saw the activation of a pre-existing fault in their system. So we like to propose that the back front that occurs post-injection is due to the activation of a pre-existing fault in the geothermal reservoir. And lastly, we begin to compare the distance versus event number rather than time, because that migration pattern changes after the 5-day post shut-in sort of migration, and we start to see more of a linear growth that follows a self-driven rupture front model. So these events are triggered by the pressure relaxation and those buoyancy forces acting on the fluids within the system. And yeah, a difference in just triggering mechanism and then therefore migration pattern is seen in that last portion of the seismicity, kind of up in that fracture zone 2B area and the shallower part of fracture zone 2A. And so just to summarize and conclude here, So we have the reactivation of those pre-existing fault structures, which we now attribute as sub-fracture zones 2A and 2B. And those fluids that encounter the pre-existing faults can become trapped within the reservoir. This decreases the efficiency of enhanced geothermal systems and can lead to can pose larger seismic hazards and risk. However, the high pressure fluids trapped in the reservoir, drive that seismic migration. This is where we see diffusion patterns during the circulation, and then a change of triggering mechanisms cause a different growth pattern in that last portion of the microseismic activity. And the backfront forming post injection is caused by the presence of an activation of a pre-existing fault. And so that's all I'd have you guys today, and I'll take questions. Thank you.